Alright, hello guys and welcome into another class. Today we'll study sequences of functions. This is an important topic if you are interested in constructing indirectly a function, a desired function that you actually cannot provide a rule of definition. So with sequences of functions we approximate step by step to a new function. So with each step we are a bit closer to our desired function, and in the limits we actually get there. So there are roughly two types of convergence of functions. One that is convergent in every point, but every point has some sort of different convergence. So there is no general rule for all of them, and that's called simple convergence. And the second type of convergence is called uniform convergence. So in uniform convergence, it's not like point-wise, but the whole function converges to the limit. So it is obvious that uniform convergence makes more properties of the functions of the sequence of functions transfer to the limit, to the function that is on the limit. Alright, so we will see this in detail in the following. A sequence of functions, well, this sequence of functions is of course needs to be defined on the same domain. All of the functions need to be defined on the same domain, and they should go from some x and into the real numbers, of course. And now this, so for every n we define as a function like that, and so this is a sequence of function. Alright, so we say that this sequence converges to some limit function that we call f, that is of course defined on the same domain if, and now comes the good part. So we start picking a point or any point of the domain, and let's say that for every epsilon bigger than 0 there must exist some index and node such that for every bigger index we have the following. Alright, so that means that if you pick some point of the domain and you pick some neighborhood of the value of the limit function, then that will happen is that there must exist some index such that starting from this, all of the values of the functions will be inside of that neighborhood. So inside of the value of the limit function on the neighborhood of the value of the limit function. All right. So if we do a graph, a quick graph. So let's say that this is the domain a and b, and the limit function is like this. This is f. All right. So we pick x0 here. Right, so this is f of x, and we choose our epsilon, a neighborhood like that, and from some n0 all of the values of x of f and of x0 should be inside of that neighborhood. Alright, but what happens if we choose another point of the domain, x sub 1, let's say, and we keep the same value of the neighborhood epsilon? will the index be the same? Well, there is no reason for it to be the same, and in fact it may be different. So for different points of the domain there may be different indexes from different indexes from which we have this property. So that's a problem. It is a problem if you want to define properties on the limit function. So well, this property happens because this definition of convergence is too weak. So we need to strengthen this definition, and the stronger definition is the following: is that definition that convergence is called simple convergence. And we also have uniform. Alright, so uniform convergence is not about having one index for every point and every epsilon, but for all of the domain, and particular index works. So how is that? Well, instead of choosing here, let's copy that. Alright, so let's erase this, and we have, alright. Alright, so for any epsilon bigger than 0, there exists some index such that this works. But now we will say that not only for every one of them, but also for every point of the domain. So this makes a lot of things easier in the following sense. Now we have, that's so awful. Alright, so we have our domain here, we have our function like that, and now our neighborhood is not defined for x, but for the whole function. So it's like we cover our function with a code. So let's say we surround it. Right, so this is our neighborhood now that covers the whole function f, and there exists some index starting from which all of the values of the functions will be inside this code. All of them will be here, starting from this, so and so on, right? So this is uniform convergence. Many of the properties of the functions, of the sequence of functions and uniform convergence are transferred to the limit function. Properties like continuity are easily transferred. So we will see that in the following. It is actually easy to see why, because we can do it here quickly. What happens if all of the functions are convergence in a single point here? All of them are convergent here, are continuous here. Will the limit function be convergent? The answer is, of course, it will be. And how will that be? Well, we pick one of the functions, let's say f, like this particular one, and this is continuous. So we are under the assumption that that all of the functions are continuous on this point x0. So this will be continuous on x0. So that means that there exists some delta positive, such that if x is in this neighborhood, then this means that is inside this is a bit complicated. All right, so what does that mean? Well, this is the point f and 0 plus 1 x0. So we are using a smaller neighborhood because we will see why this is. So we will see that there's a neighborhood here, epsilon divided by 3 neighborhood, and this is our delta neighborhood here. All right, so everything that is in this neighborhood is mapped to this neighborhood, to this small neighborhood. All right, and so we want to show that for every x in this neighborhood, f of x will be inside this one. And how is that? Well, because you see that this is if and only if f of x minus is smaller than epsilon, right? But you see that we can add, well, subtract and add, subtract once again and add. This is like a game. And the remaining term, right? So we made no change, this is the same, but it happens that this is smaller or equal than, you know, the triangular rule. Right, so we put this here, we put this here, and we put this here. I don't want to write it again, but you know that this is the difference of f and this function on the same point, and all of the functions are inside of this code, right? But if we made this code like that, then this will be smaller than epsilon divided by 3. Now here we have this difference of x of the same function but with different value, but we are under this case because x was taken here, so this is happening, right? So this is smaller than epsilon divided by 3, and the last one is the same as the previous one because it's the same point, different f, same point. So once again we are under this case, so the function, all of the functions are, or all of the values of the functions are inside of the epsilon divided by 3 neighborhood of f. So this whole thing is smaller than epsilon, and this is, and that's how we get here. Alright, so that means that the function f is continuous on this point x of 0. So we concluded that if in fact we don't need that all of the functions are continuous on that point, but that all of the functions is starting from some point onwards are continuous on x naught. And yeah, so if all of the functions starting from some point are continuous on the domain, then the limit function f will be continuous on the domain, so it will be continuous. So there are more properties about that are transferred, like some properties about integration and more interesting stuff, but this is an introduction of of this topic. If you're interested, well, keep watching the following video because I will surely update it, and see you around.